Hello everyone, I'm Zili from Tsinghua University. I'll be presenting our work interpreting deep learning-based networking systems. This is a joint work with Minghu, Jiasong, Mingwei from Tsinghua, Hongzi from MIT, and Hongxin from Clemson. Before talking about interpretation, let's first give a quick look at the existing deep learning-based networking systems. With the emergence of deep learning, many networking systems start to employ deep learning algorithms, and some are even being deployed in the industrial applications. And the reason is quite straightforward. Deep neural networks can offer much higher performance than the heuristic algorithms. This work has performance improvements of around 30% on average. However, when deploying deep learning in networking systems, operators might confront a series of problems. The first is how to design the neural network structure themselves, with very limited knowledge in deep learning. From the view of network operators, how can we design a neural network to connect observations and possible actions? A naive solution might be a fully connected neural network, which is actually adopted by several projects on the last page. Another design choice would be putting some critical variables near to the output layer. Okay, so a third design choice might be adding some pre-processing units to some inputs, and there could be much more candidate structures. Note that, despite they are equivalent, we will consider the neural network as a black box. The fact is that neural networks with different structures have different training efficiency, which will affect the final performance. Network operators might not have enough knowledge to decide which structure is better. The second question is how to debug and fix the problems of DNNs. Let's look at this example. The x-axis is different actions. They can be the scheduling decisions of flows on a switch, and the y-axis is the distribution of different actions made by the DNNs. Now something seems not working well. One of the actions is almost not chosen. So there might be something wrong with the decision-making algorithm. So if a decision-making algorithm is a conventional one, say the shortest job first scheduling, operators might realize that, it's a starvation, by discovering that it's always the longest job that is not selected. Therefore, they introduce the aging mechanism and fix the problem. But when it comes to a deep learning-based algorithm, due to the massive number of neurons, how can network operators know which part of neural networks goes wrong? The third question is how to deploy those systems onto network devices. The first barrier is the resource consumption of neural networks, and specifically the resource consumption at the inference stage. Many networking systems are deployed on in-network devices, such as switches and middle boxes, or on end devices such as mobile phones and smart TVs, and many of those devices are resource limited. For example, when we are trying to deploy a DNN onto a data plane of a switch, we can only figure out that even doing flow number calculation is very difficult. Needless to say, deploying a neural network, the computation ability, memory, and storage of network devices do not match the need of deep learning. The second barrier is the long decision latency of neural networks. Let's consider a case of deep learning-based data center switch scheduling. If network operators want to optimize the scheduling decisions at the per-flow level, what would the control loop be like? When the first packet of a flow arrives, the switch will report the information of the flow to the neural network. Then it will compute the scheduling result. The inference of neural networks usually takes tens of milliseconds. And during this time, packets of this flow are still being processed by the switch with some default rules. When the scheduling decisions finally come back after tens of milliseconds, most flows in the data center have already run out. The performance of deep learning-based networking systems might therefore be degraded. Finally, operators might do frequent ad hoc adjustments to the existing rules of networking systems, such as routing reconfigurations. One more question would be how to ad hoc adjust the DNN-based rules according to the specific requirements. Let's see an example of a deep learning-based routing optimizer. The neural network has already decided the routing path for two flows as shown in the figure. Now the network operators want to migrate flows from the link between node 7 and 10 due to some reasons, such as pricing or maintenance. If it's a conventional routing algorithm, such as the shortest path routing, network operators can just recompute the second optimal path for those affected demands and reinstall the routing rules. But if it's a deep learning-based routing algorithm, can we simply recompute? In the shortest path algorithm, the routing decision of a flow will not affect another flow. But for neural networks, this cannot be guaranteed, since they are not stable and robust to the input. Other unrelated flows, such as the green flow in the figure, might also be affected in this recomputation and need to be migrated, which will increase the migration cost. Well, manually adjusting the routing paths is also very difficult, because we do not know why the DNNs make such decisions. Neither do we know which candidate path is better. So now we know that DNNs are difficult to design, deploy, debug, and ad hoc adjust from the view of network operators. And the root cause is because network operators could not understand why deep neural networks make such decisions. And moreover, it could become more and more difficult to understand. The application of DNNs in networking systems is still at a preliminary stage. The first successful application of DNN in SIGCOMM was just published 3 years ago. So let's see what happened to other communities that are using deep learning earlier than us. For example, the natural language processing. We can see that the number of parameters of language models has been keep growing exponentially in recent years, from millions of parameters to billions of parameters. And the recently released GPT-3 model even reached a surprising number of 175 billion parameters. With the similar development from the other communities, larger DNNs in networking systems in the future will further aggravate those problems. So what if we can interpret the behaviors of deep learning-based networking systems, and therefore speculate how and why they make such decisions? Thus, I'm going to introduce METIS, a general framework that provides interpretability for networking systems, and therefore sheds light on the problems above. So here's the challenge. As we can see, there are many scenarios under the umbrella of networking systems. How can we interpret those diverse systems? Are there any similarities among them? Our observation is that we can briefly categorize them into two types, local systems and global systems. Local systems collect information locally and make decisions for one instance only, such as the congestion control agent on end devices. And global systems aggregate information across the network and make global planning for multiple instances, such as the software-defined network controller. For local systems, we find that existing policies are usually rule-based with a simple decision logic. Therefore, our solution is to convert the neural networks inside those local systems into simpler and self-interpretable models. According to the recent advance in the machine learning community, there are many candidate models that could be the target of the conversion. Our design choice is to convert those policies into decision trees. The first reason is that decision trees are non-parametric and can represent very complex policies by design. The second reason is that decision trees are lightweight enough for networking systems, which we will later demonstrate. Moreover, the structure of decision trees also resembles the rule-based essence of local systems, such as the routing table. Therefore, we adopt a conversion method based on a teacher-student learning process. Operators still need to train the DNN first. The high-level idea of the conversion is that the DNN acts as a teacher and generates input-output samples to construct the decision boundary in the state space. The decision tree is therefore constructed according to the samples of the DNN. And for more algorithm details, please refer to our paper. For global systems, our observation is that we can formulate many of them with hypergraphs. So what's a hypergraph? In the traditional graph, an edge connects two vertices. And in a hypergraph, a hyperedge can cover multiple vertices. So why can many global systems be formulated into hypergraphs? We find two outstanding features of global systems: the graph structured inputs or outputs, and the bivariate mapping. Graph structured input-output means that the inputs or outputs of global systems are graph structured, such as the network topology. For example, in the routing results of a deep learning-based routing optimizer, we can formulate the interaction between routing passes and links as the relationship between hyperedges and vertices. Bivariate mapping means that the global system constructs a mapping between two variables, such as allocating resources to requests. In such case, the two variables can therefore be formulated as node and hyperedge. With the hypergraph formulation, the next step is to find out which connection between hyperedge and node is critical to the optimization result. In the interest of time, I can't go into the details. The high-level concept is that we calculate the importance to the optimization goal of every connection in the hypergraph. Network operators can therefore use these information to understand why DNNs make such decisions, and to make sure that the interpretation results could be understood by operators. We have three metrics to measure when calculating the importance of every connection. The first metric is the performance degradation. The critical connections found by Mattis should be those connections that have a great influence on the output of networking systems. The second metric is the interpretation consistency. Usually the number of interpretations that humans can understand is budgeted. Therefore, the number of critical connections should also be concise enough to be understandable for network operators. And the final metric is the determinism. That is to say, we expect each connection to be either critical or not critical. Otherwise, the crafty agent will learn to allocate all connections with the same importance and generate meaningless interpretations. Now I will show you a wide range of experiments that we did. We implemented Mattis onto 3 deep learning-based networking systems, including Pensive, an adaptive bit rate system, and Auto, a switch flow scheduling system, and also RoadNet, a networking optimization system for the software-defined networking. 2 of them are local systems, and the remaining one is a global system. The interpretations of Pensive, as presented on the slide, is a decision tree. We can clearly see the decision logic of Pensive. On the top 2 layers, Pensive first classifies inputs based on the last trunk bit rate, or RT, which is different from existing methods. Mattis discovers that the information contained in the RT affects the performance significantly. Later, Pensive makes decisions based on buffer and throughput, similar to existing heuristics. For interpretations of other systems, please refer to our paper. We further show how Mattis addresses the problems introduced in the first part of this talk. As we interpreted it before, Mattis finds out that Pensive significantly relies on the last trunk bit rate, or RT, when making decisions. To utilize this observation, we modify the DNN structure of Pensive to enlarge the influence of RT on the output result. We concatenate RT to the output layer so that it can affect the prediction result more directly. After putting RT near to the output layer, the modified DNN will focus on that significant feature. We evaluate the quality of experience, or QoE, of 2 models. From the curves of the original model and the modified model, we can see that the modification improves both the training speed and the final QoE. The second case is how Mattis helps operators to debug Pensive. Pensive is known to have the problem of missing bit rate. We reproduce this problem in our experiments and present the frequencies of selected bit rates by different algorithms. But when it comes to Pensive, 2 bit rates are missing, with an extremely low probability to be chosen. This phenomenon has also been mimicked by Mattis. When the agent discovers that using 4 actions only can achieve a good reward, it will abandon the others to maintain high confidence. This makes Pensive fall into a local optimum. Without Mattis, operators may have to retrain the DNN model from hours to days, without knowing whether the agent can escape the local optimum itself or not. The conversion from DNN to decision tree in Mattis exposes an interface for network operators to fix the problem. Since the dataset to train the decision tree is highly imbalanced, we oversample the missing bit rates during the conversion. Compared to the original pansing, the oversampled decision tree outperforms by about 1% on average on two sets of traces. Note that even 1% improvement on QoE is significant to current internet video providers, considering the volume of videos. We further introduce a case of how Mattis helps to deploy on the case of Auto, which is a deep learning-based data center flow scheduling optimizer. The per-flow decision latency of Auto is 62 milliseconds on average, during which 94% of short flows in data centers will run out according to the statistics in DCTCP. Converting DNNs into decision trees enables us to make per-flow decisions for more flows with a shorter decision latency. In this case, Mattis together with Auto can cover 39% of flows on the same traces. Precise per-flow control on more flows will also improve the performance of the system. By covering more flows, Mattis together with Auto can improve the average performance by around 2% to 5% on two traces. More detailed analysis show that the improvement mainly comes from the optimization of those median flows, which are newly covered by Mattis. Finally, we have a case on how Mattis helps network operators to ad hoc adjust the root net system. Suppose we have a flow from node A to node E, and it needs rerouting away from the original path P0, and there could be several candidate passes, such as P1 and P2. The actual performance of each path is unknown until the rerouting rules are installed. Our observation is that since the candidate passes divert at different nodes from the original path, we could estimate their performance by the mask value of the connection between the diverting node and its next hop link. For example, P1 diverts from P0 at node A, and W01 is the mask value of the connection between P0 and link A to B. Since W01 represents the significance of selecting link A to B rather than other links, a lower mask value of a connection means that the selection is not critical in deciding the routing path. Therefore, lower W01 value indicates that path P1 might also have a good performance. We can thus hypothesize that the relationship between W01 and W02 is correlated to the delay of path P1 and P2. We verify this observation with the dataset evaluated in RootNet. 3/4 of points fall into the yellow quadrants, with another 19% points shaded green very close to the quadrants 1 and 3. This demonstrates a strong correlation between these two pairs of values. Thus, we provide an indicator for network operators to decide which path to reroute without estimating the end-to-end path latency. As a summary, we first demonstrate several problems of existing deep learning-based networking systems. We then design Mattis, which first categorizes diverse systems into local and global ones, and then interprets them with decision trees and hypergraphs. In our experiments, we implement Mattis with 3 systems, Pensive, Auto, and RootNet, to show preliminary cases on how Mattis can help network operators to design, debug, deploy, and ad hoc adjust those deep learning-based networking systems. More information and the open source codes can be found in our website. We do hope that Mattis could shed light on and accelerate the deployment of deep learning-based systems in the networking community. If you have any questions, don't hesitate to reach out to me. Thank you.